and has worked at NASA's Goddard Space Flight Center in Greenbelt, Maryland, USA since 1985. He is affiliated with the Department of Physics and Astronomy of George Mason University in Fairfax, Virginia since 2007. His area of expertise is ionospheric physics and space weather. He is the principal author of the International Reference Ionosphere Model, IRI, which is the International Standardization Organization standard for the ionosphere, and it is also widely used for application in science, engineering, and education. He has organized several biannual IRI workshops to discuss improvements, additions, and shortcomings of the IRI model, and has collaborated with colleagues worldwide on implementing some of the recommendations. He is currently working on improvements of the IRI model in the lower ionosphere, on its extension to the plasmasphere, and on a better representation of real-time conditions by assimilating real-time measurements of characteristic parameters into the IRI background model. With colleagues at NASA's Space Physics Data Facility, he developed the very popular interface for online computation of geospace model parameters that was later migrated to the NASA's Community Coordinated Modeling Center. He played also a key role in saving and analyzing the unique database of Alouette Isis Topside sounder measurements covering almost 2 solar cycles from the 60s to the 80s, which remains one of our prime data sources for studying the topside ionosphere. Dr. Bilitza authored and co-authored over 180 referred journal articles, served as editor for 24 special issues, and contributed chapters to 4 books. He is the recipient of the 2007 NASA Space Science Achievement Award, the 2013 Christian Birkeland Medal for Space Weather and Space Climate, the 2017 Karl Raver Gold Medal of the International Union of Radio Science, and the 2024 COSPAR International Cooperation Medal. Please, Dieter, the floor is yours. I remind to the people that is following the seminar in streaming that if they want to ask a question to the speaker, please fill out a form that is provided with the seminar. So, thanks.
Good morning. I can talk from here. It's a pleasure to be here, and I'm very thankful for being invited to celebrate the 25th anniversary of this great institute here. And so I'll be talking about the International Reference Ionosphere. Of course, this is something I could be talking several hours about. So that's why I'm focusing here on the topside and the extension to the plasmasphere. But actually, I want to start by giving you a little quiz. So I picked up 4 different publications here, very recent, from different papers. And so the top one is about tether for the International Space Station for adjusting the orbit of the space station. Then you have here GNSS, natural hazard monitoring. You have unifying the Nepal and China height systems, and you have the altimetry satellite long-term change which is important for sea surface heights and other things. So the question is, what is common to all of those publications from many different areas of science, many different publications? And I'm sure you all know, of course, it is the topic that I'm going to talk about. You can see here, if I can, here it's coming. So IRI, this is just an excerpt from these papers, IRI. So this is just 4 examples from different areas of science that made use of the International Reference Ionosphere, the model that I'm talking about, and it was an important part for doing their type of science. for anybody who got the right answer, the beautiful picture. And this is actually a picture that was taken from the space station. It's a long exposure photograph taken showing the ionosphere. Here you can see it as the reddish, greenish glow there. Beautiful, of course, down you can see the lights from Earth. Beautiful this depiction of the Earth's ionosphere. The importance, you already saw that in my little quiz, that this ionospheric model is very important for many applications because the ionosphere is a plasma consisting of electrons and ions, and it affects electromagnetic waves going through that plasma. So radio waves that are used for these different applications that I've listed here, GNSS, radio astronomy, Earth observation from space, communication, telecommunication, and then also designing and operating space vehicles and experiments, you need a representation of the ionosphere, and it should be accurate as possible so that you can subtract the effect that it has on your probing signal. So IRI, what is it actually? It's an international standard for the most important plasma parameters in Earth's ionosphere, and I'll tell you in the next slide what they are. But here it's important to point out that this was actually initiated by the two international organizations that are most important for ionospheric physics, the Committee of Space Research, which is the organization of all the national space Okay, so sorry. It is both from COSPAR, and then there's also the International Union of Radio Science, which is the, of course, the main organization that is dealing with the propagation of radio waves. So COSPAR was interested for the spacecraft to have a general description of the geospace and the ionosphere in particular because of its effect on radio waves, which are being used for navigating, communication. So for them, it was very important to have an international standard, and most space agencies actually use the IRI for this purpose. Then ERSI was more interested in having a background model for radio propagation studies, very important for telecommunication. ITU, the International Telecommunication Union, recommends IRI. And then, important point here to make is, so this organization, they requested that this be an empirical model so that it would not be depending on the evolving theoretical understanding of ionospheric processes. This is similar to other areas of geospace like the magnetic field, IGRF, like the atmosphere, ENSO. So these are all empirical models, and they are widely used in scientific research. And then we were also asked to, as new data become available, of course they become always available, to improve on the model. An important task was also to look into differences between data recorded with different techniques from the ground or from a spacecraft. And so we did a lot of bringing together the space and the ground-based community to establish, to improve on their data analysis schemes, then to come up with good agreement. This is still an aspect that needs a lot of discussion, as for example we see with the most recent Gold and Icon, recent satellites, where you always have calibration issues. So this was an important task that we were involved in. So which parameters and in what range? So what IRI describes is basically the densities of electrons and ions and the temperature of electron and ions. And that is in the altitude range of the ionosphere is from 50 to about 2000. And so the drivers that we use are the solar indices, of course, because the ionizing irradiation from the sun is responsible for creating the ionosphere by heating the atmosphere. And then we also have special ionospheric indices that are very important. They're basically recorded by the ionozones, worldwide ionozones, and then a special mathematical scheme to come up with a single index for the whole world. Again, this is similar to other, like the magnetic indices. If you're familiar, AP, KP, they're using the ground-based magnetometer to come up with an index. And we use those, AP and KP, also for the model to describe storm activities. Over time, we have added additional parameters. So this is basically at the request of users. That is the nice thing about IRI is that we have, as I told you, lots of users, and they are not shy in contacting the IRI team and asking for additional things or pointing out problems of the model. So we have added of course, the total electron content by just integrating along the profile, but also the ion drift at the magnetic equator, which is very important for anomalies at the low latitudes. Occurrence probabilities, very interesting for many applications. They want to know, what is the probability that we run into certain problems. Spread that there is an F1 layer, and we are now working also on sporadic E. A-quadrant oral boundaries, very important. I don't know if it's probably too far south, but there was a solar storm not recent, a few days ago, where the northern lights could be seen very far in and beautiful pictures. So you can look at the auroral boundaries in the IRI model, and you see there's a KP dependence, so the auroral oval expands as you have activity. And then also that most recent ratio of plasma frequency to electron gyro frequency, which is important for specific measurements. So there's a lot to talk about all of this. But yeah, the point I also want to make, because it is an empirical model, of course, data are very important. So here are all the different data sources that you have for the ionosphere, both from the ground. Of course, the ionozones. The top here, the ionozones. There is one on the right side there. There is now about over 60, close to 70 ionozones worldwide. We have but they all can only measure up to the peak, the F peak. Then we have the incurrent scatter radars. They can get measurement of the whole electron density and temperature profile, and also the ion composition. But there's only a few of them because they're expensive and they need a lot of energy. And unfortunately, we lost. There's only 9 of them worldwide, and we lost this one. This shows Arecibo, which actually became more famous through a Bond movie than through the science. One of the Bond movies was filmed there. So then we have the topside sounders. They can measure. They basically kind of carried the ionosonde into space and then looked down rather than the ionosonde looking up. And so they have recorded a lot of the topside, the area close to the point of highest density of the ionosphere. And there were the Alouette and the ISIS topside sounders. Very interesting international project in the 60s, 70s, up to the 80s, 2 solar cycles, but way ahead of his time. So a lot of the data actually were not fully analyzed at the time. If I have time, I'll talk some about this. Then we have the in situ measurements. Of course, there you have to depend on the orbit of the specific satellite. You have other sun synchronous orbit, high inclination, low inclination. So it all depends what kind of coverage you get for your modeling. Rocket data are very important in the lowest region where the satellites cannot reach, and the atmosphere is too dense to look at it from the ground. Then more recently, the GNSS satellites and the radio occultation has been a big benefit for modeling, both from basically from all the low altitude satellites. So we have used all of these data sources for IRI, and we have also, in the case of Alouette ISIS, we have helped to exploit some of the older data sources that had not fully been restored. So we did that, and then almost doubling the data volume that was available for the topside. So very important to look at the long-term trends, global change in the ionosphere. And then also, like I mentioned, we try to help with finding calibration issues from the ground or from space. Just to give you an impression, these are all the in situ satellites that we have used, going from the very early explorers to the most recent ICON satellite launched by NASA. So that this covers 5 solar cycles and a wide range of altitude and local and latitude. Very important, I have to show this slide because we are, the IRI is basically international collaboration of many people. We have a working group that is sponsored by COSPAR and ERSI, and we have members from all different countries in there. It's 68 members, 28 countries, and as you can see, we are well represented by the institute here, by Michael and Alessio and Bruno. And so we are, usually I'm showing a world map here with all the different places, but I think you can see we are all over the world. The big advantage here is, that unfortunately we still have issues with data circulation, making data available. Having all these people, we get access to the worldwide database. That is a big, big advantage of IRI and has helped us a lot. And, we have workshops going back to 1983, believe it or not. So most recently we had, just last month, the workshops are very important for the members coming together, talking about improvements of IRI and talking about collaborations between the different members. And most recently, last month, we had a meeting in Kenya at Pavani University. Very nice workshop. And we are planning to have workshop next year in Italy at ICTP. We are working with Bruno Nava, and that will be end of September, beginning of October next year. These workshops are usually two weeks. Here are a few pictures from our last one in Pavani. So the first week is all for students, and the second week then is the expert meeting. And we give prizes. This is the first prize, a winning team. They work in teams of 5 on specific problems. And we had a sponsor giving us a little bit of funding, so we can give actually financial gratification to the winners too, which makes them very happy, naturally. Again, before I get into the details, here I wanted to show you the wide range of journals in which IRI has been used, in papers where IRI has been used. We have now reached 100 different journals. You see the number here, 100 different journals. I have grouped it here very loosely in different aspects. You can see there is very different areas where the IRI model has been used. And actually the 2017 and 2022 IRI papers were the most downloaded papers in the 12 months of publication. I think that also says something. And reviews of geophysics is, of course, the AGU journals that covers all areas of geophysics. So that's a nice indication of the value of the model. But let's get into the details. Topside. First talk about the topside. This is a graph of the electron density profile as it is given in IRI. And here you have the separation. We can ignore the item on the right, the figure on the right. Just look at the one on the left. So you can see the topside is a very important part of the whole electron density profile. It covers most of the total electron content, which is the very important parameter for many applications. So topside is a top parameter for IRI to deal with. And yeah, if you look at this little space here, that is close to that is the F layer. Basically, you can show that if you use simple aerodynamic arguments, you find that the best description there is a Chapman type profile that is shown here with the plasma scale height HP. So basically you get the layer because the irradiation from the sun is absorbed, the neutral constituents decreasing with altitude, so you get the layer structure that we saw in the profile before. But this is not the only function that has been used. The Epstein function is very popular, used for topside modeling. Here it's also called the sec² function, but it is an Epstein function. It's a whole family of functions that has been used by the IRI team, the Chapman function, exponential, parabolic. You can see all the different shapes here in this paper from Stankov of 2003. So then when you fit that to data, you get an effective scale height, which is different from the plasma scale height. And of course, we have 2 papers here. Actually, one is the Annals of Geophysics paper that have looked at, that try to evaluate which one of this function is the best to use for modeling the topside profile, but the results were inconclusive. I mean, it basically said all of them are equally well. Actually, the exponential was very good, but then the exponential, of course, doesn't have the layer structure. So, and then important point, of course, if you look at the plasma scale height, it varies with height. Both the temperature and the mass of the ions changes with height. So you have to consider, in the previous slide, what I showed you was constant scale height, but you have to have a scale height that changes with height. Close to the peak here, you have the 4 different functions that I showed you Epstein exponential and Chapman and the two Chapman functions. And you can see that they are not very different in describing the layer here, because I'm using or they use an exponential scale here. But clearly you can see you're going from the mostly oxygen ionosphere to the light ionosphere, which is hydrogen and helium. So you go from 16 to 1 in M, so that is a big change in the scale height, and that big change you can see here clearly. So you need to have a variable scale height. And modelers have used a variable scale height. Just here are a few recent examples that have used this. The Epstein function is being used in the NA-QUIC model that is developed by the ICTP group, and where the members here from INGV, Michael and Alessio, they have done a lot of work on improving the model, the topside part, especially the scale height. So that is an area where there is lots of activity going on. Then Bodo Reinisch, who is the developer of the DigiSonde, he also did a lot of work in the theoretical part of the ionosphere, and he basically did go one step further. He, I told you that simple aeronomic arguments give you the Chapman, but you can also, if you assume a constant scale height, but you can also start out with a variable scale height, and then you get this more complicated formula here that Bodo Reinisch, and that some people are using now, but most people have gone back just using a variable scale height. I also want to point to this paper here from Alessio, who, if you are interested in the connection between the plasma scale height and the effective scale height, that modelers have found. Very nice paper, highly recommended. Nice read. So now let's look at what is in IRI. So IRI also uses the Epstein function, but here first a word about the data source. So the problem we have with empirical models, of course, is always we need more data. We have a theoretical understanding, and we measure because we find that there are additional aspects that have to be included in models. And so that is a big argument for having more of the measurements available. So topside sounders, for example, there has been none for several decades, an area where we are trying to strongly promote the new topside sounder satellite. In scatter radars, as I said, there's only 9 of them, and we lost a very good one in Arecibo because of the hurricane and the after effects of an earlier hurricane, not the most recent one. And then, of course, in situ measurements have their own problems. On the positive notes, we were able to double the volume from the topside, from this early mission of topside sounders. So because of all these issues and because of the importance of the topside, we actually offer in IRI 4 different options for the topside. So we recommend one, which right now is this what is called Core 2 here. But we let the user use all the other ones, and many people do, and they help us by comparing with new data. As in when a new satellite comes on, often the PI group, the first thing they go to IRI, they check how well agree the satellite data with their measurements. So we have these 4 options. They are different. Sorry, there's a lot of text here. I had to decide, do I want text? Do I want a lot of formulas? But the formulas, you know, you see it once and then it's gone. Here the text, you can more focus on specific things. So that's what I want to do here. The first version is actually the oldest one in IRI. That was done by Raver, the first chair of the International Reference Ionosphere, who died a few years ago at the high age of 104 years, quietly dying while reading a book. Don't we all want to go like that? And so he was very active, of course, and he was one of the initiator of the IRI project in the COSPA framework. So he started with this Epstein function and used the model that was widely used at that time, the bent model, based on the topside sounder that I told you about. But he basically used the Epstein functions to come up with an analytical representation. But the problem here was that it only was based on 40,000 electron density profiles from the first of these missions, Alouette 1. So it had serious issues at mostly high solar activity, where the profile almost became constant. So it was artificial, clearly not scientifically. And so I was involved in the data restoration of the ISIS data. So I used all this data to come up with a correction term. And this basically gave us the 2001 core. And then NA-QUIC, the model I talked about, is one of the options, the model that is done at the ICTP. And again, there's a number of studies also from the group in Birmingham, David Timmons, and from here, Michael and Alessio, improving on NA-QUIC. One problem here, what I've shown here, is basically the electron density altitude versus magnetic latitude. And you can see there is two peaks at lower altitudes that merge into a single peak. This is the famous equatorial ionization anomaly. And the IRI model do that quite well, but you can see that the NA-QUIC model has this problem, and we all know about it, that it propagates this effect at high altitudes here, which is not scientifically correct. It should be merging here. So they both have a little bit of issues still. And then most recently, I have worked with the Potsdam group and with Jiang, who is now back in China. Well, I should start out. So the Potsdam group, Hermann Löhr and Zhao Qiang, they found that IRI was actually all of these three options were overestimating data from the Swarm satellite, from the CHAMP and GRACE satellite, and then later they also were involved in the Swarm satellite. And this was basically because in 2008, 2009, we had solar minimum that was very unusual, very low values of F10.7 and a very extended solar minimum. So conditions that we didn't have before, and that's a problem of an empirical model, depending on data. So if you didn't have data for that from earlier times, you couldn't model. It's not in the model, and this is what happened here. And this was actually a big deal. This was in GRL, Geophysical Research Letter, and then was also in the EOS transaction. A lot talked about that IRI was overestimating. So important that we got all this new data, JAMP, GRACE, and started to work on improving the model and working with Jiang actually. I was able to come up with a correction factor, solar activity dependent correction factor for the model, which then helped to alleviate that problem, which is shown here. I don't know if you can see this. So you have the old IRI are the dashed curves, and the new IRI are the solid curves, and you have here Jamp is black and Grace is the blue curve, and then later on you have Swarm. And you can see the solid curves are now very close to 1. This is the ratio. This is actually the percentage ratio between the data and the model. So very good agreement with this new version of IRI, which is called IRI Core 2. And then very recently, we had the paper by Alessio, with everybody involved who is doing topside modeling. And what you can see here is basically all 4 different options. IRI 2001, Core 1, NA-Quick, oh, I'm sorry, yes, NA-Quick, and this is Core 2. So you have the ratio here, so the closer you are to 1, the better, and you can see the improvement. Here it's against solar activity. You can see the improvement going through the different versions of IRI 2001, and you can also see that IRI Core 2 and NA-Quick are quite good, but there's still solar activity dependence in both of those models that needs to be taken care of. And here on the right side you have the against the latitude, the same points can be made here. Here's even more characteristic improvement from the first IRI 21, I'm sorry, to Core and to Core 2. And NA-Quick and IRI and Core 2 are very similar. So this is a huge amount of data from the DMSP satellites at 830 to 50 kilometers, and then up there it's Grace from 40 to 50 kilometers. So this is a lot of data to evaluate these models. And here, just to give you the image, now it's showing the image of this ratio against the globe. I mean, sorry, this is on the left side you have the latitude y-axis, day of the year is the x-axis, and on the other side you have latitude and magnetic local time, and just by the colors you can see the improvement going over these different models, but also that there's still work to do. Plasmasphere, sorry, I spent a little bit too long on the top side because it's such an important part. The Plasmasphere is a more recent extension of IRI. What had been, and you know, I just included here a very early paper from an IRI session. And you can, just looking at the names, I'm not sure, you may not familiar, but this is a who is who of who measured and modeled the Plasmasphere at the time of this paper from 1981. And this is in one of the COSPAR publications at the time, Advances in Space Research, basically comparing all the different techniques that were used to measure the Plasmasphere. So IRI, even at that time, was very important by getting people together. Then Michael Rycroft was very active in modeling for IRI. He said it in his papers, it is for IRI. Kimura at the Kyoto University was very active in this modeling endeavor. And then we have the model by Carpenter and Anderson, which is probably the most widely used model. That's why I include the formulas down here for the plasmasphere, basically depending on L, which describes the shell, the magnetic field line, and also depends on solar activity and the day of the year. Then more recent models from Dennis Gallagher, who was involved in the Dynamics Explorer, was co-I on the RIMS experiment, used this data and also PWI to come up with same formula but different parameters, same formula as Carpenter and Anderson. And then more recently we had the RPI, the radio plasma imager, who was for the first time able to go along the magnetic field time and look at the electron density, and found basically that they had to include magnetic latitude. All the earlier models were basically, they were using diffusive equilibrium, basically just a dependence on L and no dependence along the field line. So this is the first one that it includes a dependence along the field line. And we used data from 3 different measurement techniques. Dynamics Explorer was a retarding ion mass spectrometer, then CREST was plasma wave receiver, and imager, I'd already told you, was the plasma imager. So these are different data, lots of data points, as you can see here, 2 million in the in the case of CREST. And we had to basically just use that part of the satellite for the plasmasphere, and we used the plasma pause as the upper boundary where the density drops by 1 to 2 orders of magnitude, and we used this model to get that. And then if you look at the data model comparison, here you see the distribution of the percentage difference between the data and model. You can see quite not bad, the agreement between, here in the case of the image RPI for the Osogin and Gallagher, Osogin and Carpenter model, the red and the blue. The Gallagher model was a little bit off. In the case of CREST, the satellite where we had most of the data, as you can see here, factor of 10 more. Both, again, Osogin and Anderson quite well, representing Gallagher not so good. I choose those 3 models because they are the most cited models, most used model for the plasmasphere. Oops, sorry. And then, so if we go to the RIMS data, again, same point, a little bit surprising that the Gallagher model is not doing as well here because it was based on the RIMS data. But there may be some points because we are only looking at the inner plasmasphere here, and he has a model for the whole, and he has his own plasma pause model inherent in the Gallagher model. So what do we do with this? So far in IRI, if you want to go to the plasmasphere, users just had to extrapolate the topside profile. That's what's done in NA-Quick in IRI+. And you can also use TEC data and get information from that. Basically adjusting your scale height to get the right TEC by integrating the profile. And we can update with TEC data. And so we are using the Booker approach, which uses Epstein functions. That's why we are using Epstein functions so much in IRI. So what Booker basically proposed for radio propagation studies, he wanted an analytic profile. So he separates a profile into areas of constant gradient. In that way, he gets his so-called skeleton profile. Then he uses the Epstein functions to basically go analytically from one case to the next of constant gradient. And then integrating this, you get an analytic formula for the whole profile, which is shown here as the solid curve. We show all this here for the temperature, but we are now using that also to extend the topside profile into the plasmasphere. We are benefiting from that already core 2 and the IRI 2001 core uses this approach for the altitudinal variation of its correction term. So this is how it's done in IRI now. And if we do that, and we then compare again with our DE1 and the RPI data, here we do the same thing. We look at the difference between data and model, the percentage difference, data and model distribution. So in red, you have the new model, and in in black, you have the NA-quick extrapolation. And you can see that the new model now, based on actual data, not an extrapolation, provides a better fit with this plasmasphere data. So in summary, IRI is widely used. Yeah, I talked about all that. So it is a good example for what an international collaboration can do for the benefit of the wider public, because of all these applications that help technology that we now use so much that is in space. Then for the topside, we have comparable performance excellency from NA-quick and Core 2. There remain problems for both of them that I mentioned. So maybe now is time to go to a new attempt at modeling this. You could actually use the Buka approach for the topside, avoiding then making the issue that NA-quick has, that you would propagate the equatorial anomaly into the topside, upper topside of the ionosphere. So we have evaluated the most widely used plasmasphere models with data sources, different data sources. Of course, in the plasmasphere, which is even bigger than the topside, the data issue is even a more important one. There is a data scarcity, and then we use the Buka approach with fixed points at 5,000, 10,000, 20,000, and 30,000 kilometers to use then the different models at this point and use the Buka approach to get the profile. And we now have to find out how well this compares with data. And this is a first step. It is not yet including the plasma pause, and it's not reliable in the polar cap region, which is a very difficult region to model. And I think that's all I have. Oh, I wanted to point to this review paper. If you know anything else you want to find out about IRI, you can find in this 61-page paper in Reviews of Geophysics. Thank you very much.
Thank you very much, Dieter. So session is open for questions.
Thank you, Dieter. Just a curiosity then, a question. I saw in the list of the in situ data that you used for the IRI, the San Marco 5 data, and I was wondering if even the data from the previous San Marco missions are available somewhere, and why you are not using them for the IRI.
Yeah, that's a pity they are not available. I mean, at least to my knowledge. You know, I was working at the data center, and there were questions about the other San Marco data, but we couldn't find any of them, any of the different instruments. So that's why we used it, because data are available from San Marco 5.
Okay.
Maybe that was also because NASA was involved in that satellite. It was a very important contribution, Jim Betty.
Okay, thanks a lot.
Sure.
Other questions or comments? I see that there are no questions from outside, so I have a question from my side. After solving the issues with the Topside, Plasmasphere, and so on, what will be the next challenge for the model?
The next challenge, I mean, we have to resolve this solar activity issue. We don't want, if there's a high solar cycle coming up, that IRI overestimates, and any quick like this was underestimating. So that is an issue we have to find out. But maybe we want to come up with a new model for the Topside. You know, this was, this was the fourth correction of this earlier model, which was basically done by Professor Raber, who was the initiator of the IRI. So we all wanted to continue what he had started. But maybe it's time to come up with a new model that would be able to separate the top part of the upper part of the Topside from the lower F region part of the Topside, from the oxygen from the hydrogen helium part. And then Plasmasphere, Plasmasphere is just the starting point. So I'm expecting that there might be some issues. And the point here, is also, of course, there is a whole community working in the Plasmasphere. I was just now in Potsdam at one of the meetings, Yuri Spritz. And so they have their own models. We are doing this mostly to be able to do the TEC going up to the GPS altitudes, because there were so many papers that use different approaches for doing that, so then you cannot compare IRI if you use this different approach for extrapolating. But it is going to be interesting to see people now evaluating also the data part of the Plasmasphere. I think it's important also, people from the Plasmasphere, they were going down to and using IRI. But they were using IRI always evolved, when new data was becoming available. They're basically still stuck with the oldest version, one of the oldest versions. So it's important because in some way or another, the Ionosphere almost becomes like a foot point for the Plasmasphere model. So it is important to have this independent Plasmasphere fixed points that you then connect.
Thanks. Other questions?
Okay, Dieter, thank you. Mine is a philosophical question, because we have seen that recently many papers based on machine learning technique were published.
Yes.
So what is your feeling about these techniques?
Well, the Nobel Prize was given for machine learning in two different areas, and chemistry also. It's a generational thing.
yeah, of course.
It comes up at every meeting, and young scientists love doing machine learning. It is something of the future. I saw, very interesting talk from the CERN talks, which I like to watch sometimes, where they used machine learning to be able to see the movement of blood in the heart in very great detail. They needed to have a very high time resolution, very high spatial resolution, and so the machine learning helped them to focus on the areas where something changed. which would have been difficult for somebody looking. And so there are areas definitely where I think it would be important, like where it's not so good. If you have, we had many anomalies discovered in the ionosphere. What was it? Well, there's so many.
Okay.
And so that would be difficult for machine learning to discover, because they have to input the driving parameters. I mean, they have to input the parameters that then define what the dependencies are. So, if I may, just a second point. So I was talking about working at Potsdam with Yuri's group. They are very active in this.
Yeah.
They have Irina and
Artem.
Stefano working on machine learning both for the Topside and for the Plasmasphere. So I said, first point, I want to run it on my computer. I was there, I mean, I'm not joking, I was there for a whole month. At the end, we were able to do it, and only by tweaking. We had to do some things that, where you had to use a virtual version of this software, which really was only allowed to be used on his computer. So these are issues, computer issues still have to be resolved. It is, I've seen a lot of students, young scientists, showing me the Irina in Potsdam. Very impressive. I mean, to see the Plasmasphere model, you see the bulb going around, really nice. But then when you try to move it to your own computer, you run into the problems. You have to have a different version for Mac and for PC, and you have to look what the operating system is different, and then storage issues. You have to, it's usually a large volume of coefficients, you have to move that over. So.
Okay, thank you. So long life to IRI model.
If I may, one last point, because that's also important. We had little memorial in, you were at the meeting, for Leanne McGinnell, who sadly passed from South Africa. She was the managing director of the South African Space Agency, passed away much too early. She was an IRI chair for a few years. She was very active. She was already doing machine learning very early on. And at that time, we tried to put it in and tried very hard. She was the chair of IRI. We didn't manage. We wanted to do it for the peak. And so that was her goal to do, but...
Dieter, can I ask you your opinion about the physics-based model? Because I remember a paper that IRI gives better result in direct comparison with them. I don't know now if there are new comparison between these two models. IRI is empirical and the others.
Yeah, I mean, I think it's always important to have independent people doing this, because, I mean, many papers, naturally, the people who have a model, publish a paper, find that their models are the best, comparing with other models. So the CCMC has done a great job in doing that. And doing it for CEDAR, for the NSF CEDAR, they have continued. There was a recent paper, and again, IRI was doing, was the best version, even so it was a storm effect. So the problem is, if you have a theoretical model, you have to have a clear beginning of the storm, effect of the storm. If you are a little bit wrong there, you get large differences. IRI is an average. So the difference is never as large We have, of course, an average storm model in IRI. So what we have is, and every storm is different. What we have is an average picture. What they try to do in the theoretical model is to do a specific storm, and it's still not very effective. So we still have the issue with this famous, what is it called? In the neutral atmosphere, the factor that nobody really knows exactly why we have this factor. It's called after the director of NSF at one time, I forget now. Anyway, so there is a factor that has to be used for the atmospheric part to find agreement between the theoretical model and the data, the measured data. So there are still issues, and then you need both. You need the empirical models and you need the theoretical models. And in many cases, when they have used theoretical models now for operation, there is the FAME and all the different models that have been used. They use IRI to make sure that it's not above a certain boundary. You know that if you use a theoretical model and it predicts a very unusual value, you don't want that in an operational environment. You want to have some criteria, what is understandable, what should be, and then if it's above that, you want to be able to look at this data again, not use it in an operational setting right away. So I know that many of this operators, they use the IRI. It's fairly simple as lower and upper boundary of the theoretical model, but both are important. And I think machine learning is important too. And then we have a fourth group, assimilative models, where they, for example, use an IRI and then use data and use a Kalman filter technique which they use in weather a lot. They have a model part, which can be fairly simple, but then they have lots of measurements, and with the measurements they are able to assimilate this data into the model and come up with a better real-time representation of what is going on up there.
Actually, if I can comment about machine learning and other stuff, there's new direction for machine learning that is, for example, the physics-informed neural network, or techniques that use machine learning to do data assimilation. So probably this is the best way to go. So to put together physical information, data assimilation, and machine learning all together. So this is something we should work on.
Yeah, that's a good point. Yes, I agree.
Any other questions?
Thank you for your talk. I want to comment also on machine learning, and I think there's a huge gap actually between the new kids that are doing machine learning blindless and the scientists, the physicists, do what I think we have to join forces actually, and to actually use wisely machine learning and later trying to explain the physics. So instead, we don't want machine learning to replace thinking. I mean, I think we have to. No, but I think there's this gap that young are just doing it, even if we don't want to, or we are.
Yeah, I remember AGU had to start a whole new journal that is dealing with, because there was a flood of these papers coming. So at one point they actually said, I know one of the editors, he didn't want to do it any longer. And he said, if there is not one word about the physics in there, the paper is rejected right away, because he was getting so many in space physics.
Any other questions? We have time for a last one. So I have the last one.
Okay.
That is related also to this new modeling
Oh,
techniques. So
yes.
IRI code is written in Fortran 77
Yes.
because was developed in the 70s and so on. Are there any plans to translate the code in more more modern languages, for more attractive for young people?
We have a Python version, but it's already the problem that we have. The Python version is not the exact IRI, but it's the Python version of one person. So she basically would have to be in charge of updating that to the newest version of IRI, which I'm not sure if she would be able to do that all the time. There are changes. So that is the biggest problem. You know, basically, users help to improve IRI by telling us where there are problems, and then the model is being improved. There were several improvements to help the gold and the icon teams, which they were now looking at the bottom side, different hemispheres, and they did find differences. So we had to do some adjustments. Those adjustments have then to be, it's more difficult to keep the same version in different languages. You know, we did do the change. The first version was in Algol. And what was the other language? Two language, Algol and something else. Maybe it could be, yeah. And so Fortran seemed to be, the big advantage of Fortran is also that there's a community out there that helps with improvements. You know, we can always ask on the web, and you get good answers all the time. The main issue was Fortran compilers are easy to get. So people in third world countries, developing countries, they wouldn't have to pay a lot of money to be able to run like IDL or some other form of language that may be requiring compilers that are not readily available. But we like to, yeah.
Thanks, Dieter. I think it's time to move to the next speaker. So let's take Dieter again.
But we like to, yeah.
Thanks, Dieter. I think it's time to move to the next speaker. So let's take Dieter again.
Ok. Possiamo iniziare se siete pronti? Qui è tutto a posto? Ci vedi?
Sì, più o meno. Mi ha detto che è spento ancora qui. Ha vinto 66 premi, quindi rischio di schiardarmene qualcuno se non me lo scrivi.
Ok, Tommaso Alberti will introduce Professor Michael Ghil.
So, it's a pleasure for me to introduce Professor Michael Ghil, who is one of the leading researchers in the field of climate science, dynamical systems, and mathematical geophysics, I think. And Michael is now distinguished professor emeritus at École Normale Supérieure in France, in Paris, and distinguished research professor of atmospheric and oceanic sciences at the University of California, Los Angeles. And he made a lot of things in his career, mainly starting from the use of dynamical system theories in energy balance climate models, who was the first showing the existence of snowball and whirlball states in the Earth that later on have been evidenced by paleoclimate records. Then he worked also on data assimilation techniques for meteorology and oceanography, and also contributing to weather forecasting and low frequency atmospheric variability. He pioneered some advanced spectral methods, especially the singular spectrum analysis, but a lot of things. And also he extended studies on El Niño Saldo oscillations and Boolean delay equations, which are presented today. Also recently focusing on pullback attractors and extreme events, especially on tipping points and climate states. So he also received a lot of awards. In 1988 was named Fellow of the American Meteorological Society. Then he became Fellow of the American Geophysical Union in 1995 and member of the Accademia Europea in 1998. And then he received the Fellow of the Royal Astronomical Society in 2002, while in 2004 he was recipient of the EGU Richardson Medal for the Nonlinear Process in Geosciences. The next year he delivered a talk for the Lawrence Lecture at the American Geophysical Union. And then he was also honorary member for the Hungarian Academy of Science in 2010. And since 2012, he received also the Alfred Wegener Medal. So it's a pleasure to me introduce Michael, which is a colleague and also a friend. And again, for those attending in streaming, please consider to ask your question in the field which is provided below the link. So, Michael, the floor is yours.
Grazie, Tommaso. Thank you very much for this invitation. I have a lot of colleagues and friends and collaborations in Italy, but the ENGV is an institution that I'm visiting for the first time. Maybe not the last one. Tommaso and I might do some things together. So as Monty Python said, now for something entirely different. Dita, talked to us about something eminently useful and necessary and important. And I'm going to talk about the contrary. I mean, okay. Another way of putting this, I was just reminded, I don't know how many of you know the philosopher Isaiah Berlin, but he wrote a book about foxes and hedgehogs. The fox knows many things, but the hedgehog knows one thing very well, how to roll up and defend himself. So this is, more of a foxish talk. It was, incidentally, in that long list of things that Tommaso mentioned, it was a topic of my Lawrence lecture at the AGU. The paper that goes with the talk actually... I forgot to take this very important object. Okay, so is supposed to be honoring the memory of Ilya Zalyapin. I don't know how many of you who work on earthquakes I have to, sorry. Yeah. Okay. How many of you here who work on earthquakes know the work of Volodya Kailis-Bork, RIP? Ilya, when I was director of the Institute of Geophysics and Planetary Physics at UCLA, well, my predecessor and very esteemed colleague, Leon Nopov, suggested to me to hire Volodya, who had founded the International Institute of Mathematical Geophysics and Experimental Earthquake Prediction of the then Soviet Academy, and he brought Ilya as a postdoc to UCLA. Unfortunately, Ilya left us in his 50s a few years ago, but he is actually, among many other things, the one who taught me to use PowerPoint. So my Lawrence lecture was largely given with PowerPoint slides that were drafted by him and finalized by me. So anyhow, he was a really great guy, and unfortunately, he's no longer with us, but the paper is honoring his memory. So I'll tell you about Boolean delay equations, earthquakes, ENSO modeling, and tipping points, and so some other collaborators here. Okay, so these are the École Normale Supérieure, which is part of the PSL University. PSL stands for Paris Science and Letters. This is UCLA, and I'm also a visiting professor in mathematics at Imperial College. The collaborators are Barbara Colucci, who was a PhD student of Giorgio Parisi, and Céline Collomb was now at NASA. Dick D was at the European Center, is actually now retired. It's very amusing to have survived some of my PhD students and postdocs who are retired now, you know. Stéphane Algat was a student I co-advised in Paris. He's now climate expert, I forget what, he's senior climate expert at the World Bank. Volodya is no longer with us. Andrew Mulhaupt is Stony Brook University and had his own company on Wall Street and does some other things. Amia Saunders, Gerard Weisbusch, and I said Ilya. So anything that you find interesting here, you can find more about at the website at UCLA and of course on ResearchGate. Before I can tell you actually what they are, the bold hypothesis here is anything you can do, I can do better. Yes, I can explain everything is Boolean delay equations. Now, I'm not a very good singer, but many of you, I'm sure, would recognize a tune from Annie Get Your Gun, where she says, anything you can do, I can do better. You know, there it's something about male and female, but she, of course, can do it better. It's by Irving Berlin and the Field siblings. Okay, so what for BDEs? So life is sometimes too complex for ordinary and partial differential equations. What are they? So they're formal models of complex feedback webs. I will come back. There were some questions about machine learning and, well, artificial intelligence and so on. In some sense, they are a bridge in that direction. But, many things which are now called machine learning, we did used to be called data-driven models, and we've been doing for a long time. So, nihil nove sub solem, etc. So, formal models of complex feedback webs, classification and major results. I'm going to skip this part. I'd like to have more questions. There's some work on Boolean delay equations on networks, in particular with applications to production networks and so on, socioeconomic applications that I'll skip here. But I'll start at Tommaso's suggestion. I used to be in the opposite order first. I started these things in connection with climate modeling, and we got to I'll tell you. the application to earthquakes came in Rome. Okay, I was invited to a meeting of the Pontificia Academia by Volodya, who was a member of the Academy, and this was in the 90s, before sustainability had become such a buzzword. So it was a meeting of the Academy about science for survival and sustainable development. Okay, and on the weekend between two of the sessions at the Vatican, we're on the bus sitting next to each other with Volodya to Castel Gandolfo. You know, that was the outing of the meeting. And I asked, well, Volodya was already interested in some socioeconomic applications of predictions and so on. That remembered a little bit that of earthquakes. And I said, why don't we do some socioeconomic application together? And he said, well, no, why don't we do it to earthquakes? And I said, oh, you mean you know so little about earthquakes? And they said, yeah, we know so little about earthquakes. So, you know, there are no models like numerical weather prediction or so. And you know that unfortunately that is still largely the case. So actually that's how we did the work that then included Ilya Zalyapin, that were two articles that applied the theory I had developed earlier in the mid-80s to earthquakes. Okay? So seismic applications, modeling theory and predictions, applications to climate modeling, so the El Nino Southern Oscillation. Incidentally, that brings me to another overlap with Dieter. You know, IRI for me was the International Research Institute for Climate and Society at Columbia. And, you know, we're running out of acronyms. There's so much activity that, okay, and so concluding remarks, bibliography, and future work. Okay, so this is actually pretty much my first slide, okay, PowerPoint slide. So it was a launch lecture of the AGU in 2005, and there was another version soon thereafter at Bad Honnef, and then at the Max Planck Institute for the Physics of Complex Systems, etc. So it was called Boolean delay equations, a simpler way of looking at complex systems. At that time, I was only at UCLA. No, wait a second, that's wrong. In 2005, I was already at the École Normale as well. Okay, so you know, here you have some of the same people. And what for BDEs? So here we're coming to it. So this is what's, the only trouble with these things is that you have to push the right button. Oops! I think we lost the pointer. That's another problem with technology, that you know, it depends on batteries. No, I think it's really no. It's that.
It's this one.
Yeah. Okay. Okay. Now it's green. It's no longer red. Okay. Okay. So this is popularly called Francis Bretherton's horrendogram of Earth system science. Okay. So this is actually a slide from pretty much the words that are now very widely used. Earth system science started with this NASA Advisory Council. You know, NASA had looked at a few planets, and somebody decided that it was maybe time to use it to look at this planet. So there was a NASA Advisory Council, which was presided by Francis Bretherton, who was a British geophysical fluid dynamicist who had been active in the United States for a while, first at Hopkins and then at UCAR. And so it was called Earth System Science Overview. And this is, you see up here, you have the atmosphere, and then you have here the ocean, and here you have the surface, the solid surface. And here, this was also very new at the time, so in the 80s, the biogeochemical cycles. And for some reason that nobody actually knows, soil development is right in the middle of this very complicated diagram. And then there were some interesting things on the sides. You know, there is something here about humans, okay, and that now occupies a much larger part within the diagram. There are solar space plasmas, you know, they weren't totally left out, but so in the corner, there are volcanoes, etc. And then there are lots of arrows, okay? And you know, how do you do all of this? Well, this is now sort of, this was Barry Saltzman, also no longer with us, in his paper on climatic system analysis, advances of geophysics. These are a lot of positive and negative feedbacks, and here is ice mass, and here is temperature. Okay, so this is sort of an ambitious flow diagram of all these things that happen in the system. And so this is sort of the motivation, okay? Maybe you have to come up to take a first look at all of this. Well, these days, of course, you have huge models that, you know, cost a lot of computer time and a lot of person time and so on, but you'd like to have some understanding on your laptop, maybe. So what are they? Okay, formal models of complex feedback webs, and then I'm going to talk a little bit about their properties. So, of course, the idea of using Boolean, they're called Boolean because George Boole was a British mathematician in the 19th century. Interestingly, there was another person who was interested in these binary systems at the time, and you wouldn't suspect who. Name was Lewis Carroll, the author of In the Looking Glass, etc. So, and interested in, I was going to say little girls, but at least a couple of siblings. Today that would be very suspicious, but it left some lovely books behind, okay, and I don't think it went beyond that sort of thing. In any case, it goes back, of course, to antiquity, you know, ancient Greeks. Yes, no, true, false, classical logic, tertium non datur. So Boolean algebra, then propositional calculus, syllogisms, trivial examples, and then came the first modern scientific application, descriptive at first, by Jacob and Monod, who got the Nobel Prize for it. And then that turned into mathematical genetics, people like Leon Glass and Stuart Kauffman and Sugita in the 60s, and then symbolic dynamics of differentiable dynamical systems, Stephen Smale, his famous book that, you know, made DDSs famous. And then, of course, machines, modern computation, electronic engineering and computer science, cellular automata, starting with the mathematician of his generation, John von Neumann, and Stanislav Ullmann, Conway, The Game of Life, Steve Wolfram, who brought it to the great unwashed. And then spatial increase of complexity, infinite number of channels, conservative logic, Fredkin and Topoly, and then kinetic logic, which in some sense is the origin of these Boolean delay equations. So this was developed by an experimental geneticist, René Thomas, no relationship to the other Thomas in mathematics. He worked in Brussels, and he called this thing kinetic logic, and it had to do with the importance of distinct delays. He was the first one to actually construct a machine that was essentially switches, but it was an analog machine, okay, not a computer. So now the extra ingredient which comes in here is the continuous time. So the variables are discrete. Actually, the easiest, if they are just binary, that I am going to show you the example of the application to ENSO is one you can have multiple discrete levels. It's very easy to do. So what are BDEs? Short answer, maximum simplification of nonlinear dynamics, non-differentiable time-continuous dynamical systems. Okay? So the longer answer is, I'm going to go through it with you. You know, it's, as my PhD advisor, Peter Lax, used to say, you can do this in the privacy of your boudoir, for those who still know what a boudoir is. Okay, so here's X, who is in the space B, which is just 0 and 1. And for delays to be present, you have to give initial data, not just at a point like you do for ODEs or PDEs, but over an interval, okay? So here is an interval of length 1, on which I've chosen x to be equal to 1. And if my equation is just x of t is equal to x at t minus 1, so I go to a point here, I look what was the value over here, it just keeps being constant. So this is a Boolean realization of an energy balance model, a model that only has equilibria. Okay, now it gets a little bit more complicated here. X of t is equal to not x at t minus 1. I go over here. It says here is equal to 1. It has to be not that, so it's 0. But by the time I get to here, okay, then when I look here, I have to look back, and it's 0, so it's again 1. So this is a periodic solution. You can have non-trivial periodic solution with something as simple as that. So now you have two x's, 1 and 2, both of them binary, and you have two delays. I told you that that's essential to the stuff. So let's just say that the delay, you always take the largest delay to be equal to 1. It's normalized to be equal to 1. So let's say theta is 1/2. So x1 is equal to x2 at t minus theta, and x2 is equal to not x at t minus 1. So let's see what happens. x1 is equal to 1, and x2 is equal to 1 on the initial interval. Okay? But it doesn't have to be constant for the entire interval. We're going to get to that in a moment, in one slide or two. So what happens if I look at x1 here? It tells me that I have to look at x2 at time t minus 1/2. Okay, so I look at x2 at t minus 1/2, okay, and it's 1. So it's equal to that. It's equal to 1 up to here. What about x2? It's not x1. So here, okay, it is not x1. But then this one changes, okay, so this one has to change, and we see that we have an oscillatory solution which has a main property of an oscillatory solution, namely there's a phase difference between the two. You know, sines and cosines differ by pi/2. Okay, so this could be a simplest ocean circulation model for which PDE solutions give oscillatory stuff. Well, that was easy enough. We got to the bottom of the first slide. Now let's see what happens next. Well, what happens next, so there was a student of mine, Dick D., who later did some real stuff at the European Center for Numerical Weather Prediction, you know, that you look now at the predictions on your cell phone, okay? So, but before he decided on doing data assimilation for his PhD, he became interested in this, and we had a paper in the SIAM Journal of Applied Math. So here it looks almost like the previous one. This one is simple, but now here comes another, what's called sometimes connective, another Boolean operator, which is a so-called exclusive OR. Okay, so the usual logical OR says it's yes if at least one of the two things is yes, and if both are yes, but this one is only in the case in which the two agree. And theta is irrational. So what happens now, it's going to be difficult to compute in the privacy of your boudoir without a laptop, at least this thing, but what you get is this is the time axis, and this is x1, and this is x2. Well, here they start out as 1 and 0, but it doesn't matter. What you observe is the number of jumps increases with time. So this really made it fun, and it was worth publishing in a math paper. And furthermore, we actually showed that there's a lower bound on the number of jumps. Okay, so this is not just an accident. We stumbled upon it by accident because irrationals are dense on the real line, okay? But it's a property, okay? So the increasing complexity is clearly, common to any kind of evolution, biological, cosmogonic, historical, but how much? Well, okay. So here is now, well, as I said, Dick went on to do a useful thesis on data assimilation, okay? But Andrew Mulhop did another thesis, which was on Boolean delay equations, because they were sort of fun. So this is now just one equation, xt is equal to xt minus 1, exclusive or xt minus theta, and theta is a so-called golden ratio. We all know about the golden ratio, you know. So at the same time, it is what's called the most irrational number, because the convergence of the continuous fraction expansion is slowest. And what you see here is that you have essentially both an increase in number of jumps in the mean, okay, but also oscillations. So this is actually log periodic. At the time when this was published, that was not as common as it is today. It was made common by people who said that log periodic oscillations are what's now called early warning signals for monetary, for financial bubbles, you know. It's no good, okay? So actually Didier Sonnet, who for a while was a colleague in my institute, some other people who worked on what was called econophysics made this famous log periodic. Okay, here's just one that you might find familiar. You know, this is a particular version of the geological time scale, and you see that essentially the density of events is logarithmic. Now, you might say, well, but that's because we lose track of stuff. You know, sediments tend to densify. There's actually a lovely page in Thomas Mann's Joseph and His Brothers, in which he describes coastal line as having such a property because things get lost in the fog. But it is not only that, okay? There is actually a tendency, you know, in history also, you might say that we know less about early events, but there is actually an acceleration. Well, I don't know how, I mean, Tommaso warned me that the density of mathematicians here is not, you know, very large, but so I'll go about this pretty quickly. You know, these are actually occupying a place in the framework of dynamical systems that was not occupied before. You have what's called flows, in which both a state is continuous and time is continuous. So that's the ones that you are, if you are familiar with any of this, you are familiar with ODEs, PDEs, also functional differential equations, stochastic differential, etc. There's maps in which x is continuous but time is discrete. There are automata in which both x and t are discrete. So Turing machines, real computers, cellular automata, etc. And then there are these things where the state is discrete but the time is continuous. And the connections between them are, I won't insist on this too much. You know, this represents simply from here to here you have a Poincaré map, and the opposite is a suspension, and there are some connections here and there, but not as good. Okay, so I'll go very quickly over this, and I have no more further slides on the math part of this. Basically, you have a classification into conservative and dissipative, which is essential for differentiable dynamical systems. Conservative are Hamiltonian, are things like this: x of t is equal to not xt minus 1. Dissipative is x of t is xt minus 1 and xt minus theta, where theta is not equal to 1. And again, this you can do in the privacy of your boudoir. You'll see that you'll get more and more zeros, okay, no matter what you had in the initial distribution. So the analogy with ODEs is that basically in phase space, you know, conservative or Hamiltonian systems have an infinity of closed orbits and no transients, while dissipative, you have limit cycles and attractors, okay? So there's a counterpart of this in the world of Boolean delay equations. So there's a theorem that says BDs with periodic solutions only are structurally stable. And conversely, structurally stable means that if you perturb the parameters a little bit, in this case the delays, you obtain the same behavior. So the interesting thing is, because I'll come back to this at the end about the connection to the possible application in a world in which machines play more and more of a role, is that you have so-called meta-theorems that say the asymptotic, first of all, asymptotic behavior means in general as you go to infinity, but in these systems it's in finite time. Asymptotic behavior occurs in finite time, which makes it much more useful. So you have this sort of thing. The asymptotic behavior is given just by this. And you can describe the asymptotic set by an equation, which you cannot do in the world of differentiable dynamics of systems. So if you have this inequality between the two delays, solutions are asymptotically periodic. If it's the opposite inequality, the solutions tend eventually, we call this, in other words, asymptotically finite time, to zero. Therefore, as theta passes through, changes from being less to being larger than theta, one has what's called a Hopf bifurcation, a transition with persistent solutions, constant solutions to oscillatory ones. Okay. Yeah, we are doing fine. So, seismic applications. So that's work that we did with Volodya and Ilya. Basically, there was a paper by Andrei Gabrielov, Volodya, Bill Newman at UCLA, and Ilya, and Fizrev E, that looked at such a hierarchical tree on which you have one element that has 3 children. Okay, so you apply the load to this, and the children fail or not. And so you have loading by external forces, elements' ability to fail and heal. So here are siblings, okay, that in turn each have children. And so you have the load that acts from the top to the bottom and the failure that propagates upward. So a so-called colliding cascade model. And the amusing thing is that the Boolean delay, so the discussion on the bus to Castel Gandolfo was that essentially once you have several levels, you know, remember you have 3 to the power L, where L is a number of levels, you have a lot of ordinary differential equations to solve, which at that time, you know, in the 90s was still difficult to do. So I said, why don't we formulate this Boolean way? And you see that you have the same characteristic behaviors as you have in much more complicated models and in observations. So this is the magnitude, how far up in the hierarchy you get, okay? And you have high, you know, here you reach the top level. Here we had 6 levels, say we had, so 7 and so on, doesn't matter. You know, every approximate period, you reach the top. At the bottom, you have just low seismicity, noise. Everybody's happy, you know, you wake up at night, but you don't have to get out, okay? And this is intermittent seismicity when you reach the top, but you don't know when, okay? So furthermore, here we can do what's called a regime diagram. So the parameters here are the loading time at the top and the healing time at the bottom. And you see that these regimes are here high, low, and intermittent. And there is a triple point. Okay? So this was already the Boolean paper. And so if you take a circuit here, you see that the transitions are from A to B, from high to low, and then from low to intermittent, and then from intermittent to high again. Okay? Now, I'm jumping in the interest of time, the application to prediction, but really, Volodya didn't want us to do the first paper, which was just a qualitative description of what happens in such a. Now, he really wanted to go to prediction because he had this idea of what he called PSPs. What are PSPs now? Preliminary seismic patterns, okay? Premonitory seismic patterns. So it turns out that you had cascades of such patterns which led up to the highest level, okay? And I'll say a word or two about the socioeconomic applications and the analogies, but yeah, I'll do a little bit about the applications to climate modeling. So since there might be fewer people here who know about ENSO, well, this is a so-called descriptive version of the evolution of an El Nino event. So you all know that El Nino is what happens when the waters off the coast of Peru get warmer in the eastern tropical Pacific, and that's because the upwelling subsides, and so the fish don't get fed, and the fishermen don't get to eat. But aside from that, ENSO events are important because they affect weather way all over the globe, essentially. So here you go from top to bottom. Here you start having this warming up of Peru. That tongue of warm water extends across the tropics and intensifies, and then it collapses. So these are sort of relaxation oscillations, and what attracted me to this problem, of course, at the beginning, is the intriguing thing that it's clearly phase locked to the seasonal cycle. You know, they are called El Nino because they peak in December, January, February, in boreal winter, but they occur irregularly, okay? So, but that's another story that I won't go into too much. Okay, there are scalar time series that capture this variability very well. Okay, it has to do with the so-called changes in the Walker circulation, where air rises over the maritime continent and sinks over the eastern tropical Pacific. Okay, and so the interesting thing again, although it's a very rich and irregular phenomenon, there are two variables which are apparently totally uncorrelated, but in practice they're almost locked to being opposite. One is a so-called temperature of a particular part of the tropical Pacific that is called the Nino 3 area, and the other one is a Southern Oscillation Index, which is essentially the intensity of the difference in sea level pressures between what used to be Batavia at the time when it started being observed and is now Jakarta. And there's no such point over here, so you have to take Tahiti, which is not quite in the right place. But anyhow, be that as it may, these are incredibly anti-correlated, you know. So this says, in a sense, that no matter how complicated it is, there are these indices that capture much of the variability in the phenomenon, okay? So here we took 4 levels, not just intense El Nino, and intense La Nina, but 4 levels. You know, this is a histogram, which is due to Pascal Yu. Okay, this is intense and this is weak, and again this is weak and this is intense. Okay, and so the Boolean delay equation model is in the atmosphere you have wind anomalies. Again, the correlation between these was first defined by Bjerknes, who was the founder of the meteorology department at UCLA. Jakob Bjerknes, the son of Willem Bjerknes, who started the so-called Bergen School of Meteorology. So you have the easterly winds at 2 levels, strong westerlies, mild easterlies, strong easterlies. And then in the ocean you have likewise, and so you have T1 and T2, peak warming, mild cooling, and peak cooling. And the delays have to do with wave adjustments that have to do with the traveling of Rossby waves from east to west and back as Kelvin waves from west to east, and so-called local feedbacks between the temperature in the atmosphere, or the wind in the atmosphere, and the temperature in the ocean. Sorry. So the interesting thing is that you get, now this is the three-dimensional diagram, okay? Yeah, that's, okay, so here are the two delays, the wave delays, which are relatively short, and long, and the local delays, which are shorter. But basically, the average periods form what we call the devil's bleachers. Bleachers are the things that you have at the stadium, you know, where people sit on. So this is 1, 2, 3, 4, 5. So that's basically the approximate periodicity, if you average over many cycles, is of 4 to 5 years. And there's another one between 2 to 3, but I won't have the time to go into that. Okay. So, So it turns out that this is reproducing very well with this very simple model. This is now a model that has a partial differential equation along the equator, okay, and includes temperature and velocities and all sorts of things. But basically, so the two parameters here are the coupling parameter between the atmosphere and the ocean in this model, and this is a depth of the thermocline, which essentially determines the period. And you see that you have, you know, period 1, 2, 3, 4, 5, and where it's not a color but gray, it's chaotic. So basically, what happens is in the model, when two of these platforms of say 4 and 5 years overlap, the model is confused and gets chaotic. Okay? But the very interesting thing is that the simple Boolean delay equation model has essentially the same behavior. Okay? So, as I said, I'm skipping here socioeconomic applications, which involve the applications on large networks, and go directly to the conclusions. Well, this is interesting, but what does it all mean? It clearly needs more work, and that's why I'm talking about it, because I'm trying to infect some of you with a bug. I think it's very interesting, and you still don't know about earthquakes. Sorry about that, not my fault. So here are some pertinent references. Again, this is one, these are in alphabetical order, not chronological, but economic networks, heterogeneity, induced vulnerability, and loss of synchronization. This is some work by other people, Boolean delay equation model of an interdecadal Arctic climate cycle. This is, okay, this has to do with the networks, etc. And again, you know, here are the two papers by Ilya Zalyapin. So thank you very much.
So thanks, Michael, for the interesting, as usual, talk. Any kind of questions from the audience?
Thank you very much for the talk. It's Marcello Petita from University of Roma Tre. Yes, I have several questions. I will start from some of the things that we discussed also in a project that we had in common, TIPES. So how this could help us to identify the moment in which tipping points are approaching in climate systems or in other systems. So what could be the relationship between this approach and the early warning of tipping points? Thank you.
Well, let me first say a few words about you know, the analogies. I mean, one thing that Volodya was interested in is something that's called in the social sciences the broken window hypothesis. The idea is that when you walk in a neighborhood and you see a lot of broken windows, maybe things are not going to be that good. and then next you see a lot of garbage dumps being lit and so on, and finally you get a lot of criminality. Okay, and it's interesting that he introduced to me actually a very educated French woman who, after she had done the École Normale, but then for some reason became interested in being a police officer, and she became famous or infamous in France for advocating this way of supervising the danger of criminality, and of course that was terrible, as opposed to trying to prevent it by spending some money and so on. So, as soon as you get to social sciences, things get more complicated. But in any case, there is some point that would be common to. Now there's a lot of literature in the climate world about early warning signals. And it's not this, but it could be this as well. The main point that I was trying to make since the beginning, since we had gotten already to talking about machine learning and so on, is that I try to emphasize, although I don't expect that you were able to quite follow the line of reasoning, is that first of all, these systems have what we call eventual behavior, asymptotic in finite time, that they have simplification which can be explicitly modeled. We know about in differentiable dynamic systems that you have attractors for dissipative systems that have lower dimension than the full phase space, but you cannot necessarily formulate equations for those attractors. There's no simpler equation for the strange attractor, say for the Lorentz attractor. You still have to work. So this would explicitly tell you what the model is for that behavior. And then I haven't carried this out. I mean, for me, it always depends on finding some nice gals and guys who help me learn about things, and I haven't quite found those for this. But I think that with the increasing computing power, as opposed to the kind of data-driven reduced models that we had before, we could have Boolean models that would be data-based, that would be quite interesting and would have such behavior that warns of imminent disaster. That's a general idea, but
Yep.
No? Sorry, exactly on this point that was quite interesting. So the delay time is the things in which you have to work when you try to simulate something. How machine learning could help in identify the delay times that you use in the Boolean approach? Did you try in
first of all, one thing that I didn't have the time to really talk about is this think about asymptotic simplification, that fairly complicated systems can have attractors that have simpler equations. But the other thing is that you only need to determine a small set of parameters, which are the delays. If you look at Barry Saltzman's diagram, okay, there are lots of parameters, even for a simple system of ODEs, that you need to know. So here you just need to know the delays. First of all, you get a pretty good feeling of what the order of magnitude is from just observation and the basic physics or whatever it is, biology or so on. And then you can sharpen it by the data, okay? So the counterpart, the counterpart of parameter identification in the estimation and control literature for differentiable dynamical systems would be much simpler, I think.
Any other questions? I have one, Michael. So, you know that many physical systems in the real world present some kind of log-scale phenomena, no? Because usually people make spectra and see some scaling law turbulence and everything.
I know that now. Once you've said bubbles, I mean, you got a machine.
Yeah, exactly. So my question is that if we use, for example, so depending not only on the delays, but also on the number of variables that you should consider to model this one. This could depend, for example, on the fact that when you have some kind of logarithmic behavior in the spectra, you have different regimes, and then it is how much related with the number of variables that you should use, the minimum number or something like that.
I don't think that the number of variables is the thing that matters, because it's the fundamental behavior that matters. I mean, this is one of the difficulties with the IPCC process. I mean, again, I have to remind people who are not familiar, when you see an I, you think that that's international, but the I there is intergovernmental. All these governments who've signed the Rio Convention have to be represented there, including Saudi Arabia. The concept of a hierarchy of models, which got formulated in the climate sciences back in the 70s in a paper by Schneider and Dickinson, and then people like Isaac Held and myself, and has almost gone by the wayside. I'm fighting this with a former student and now colleague of mine at Imperial College, with Nature and Science and so on. We have a little paper that shows that there is really a very big danger of a tipping point upwards. The truth is that aside from the so-called runaway greenhouse that occurred on Venus, but is very far away on Earth, there were tipping points downwards toward a snowball Earth, okay? But our model says very clearly this would happen because of something that is not yet in the big models. And the editors send it back because they say, if it's not in the big model, it can't read. Okay, so because it's not in the big models, your little model is not robust. The whole point is that it's not in the big models because it takes a long time to put it into the big models. Okay? But there is some, as I said for ENSO, the fact that there are two indices which are in principle independent, that are so highly anti-correlated. The papers that were written about it being finite dimensional are ridiculous, because we can talk about that over lunch. But this one, which is not Grasberger, Procaccia, or whatever, which is just you look at it and you see it, says that there is something that is robust, that has a big importance in the whole phenomenon, okay? So I don't think that it depends so much on the number of variables.
Yeah, mainly I think that the main problem is also that sometimes you show something on complex system, which is sometimes interpreted as complicated or, how to say, high dimensional.
Yeah.
For this reason, you show a complex behavior with a one-dimensional
No,
equation.
I mean, there is actually, at the time when this thing about finite dimensionality and fractality became popular, I think roughly in the 90s, there were two papers that were published, and I think one in Nature and the other one in Science. I won't say by whom, because they're friends in both cases, But they were clearly silly, okay? Said climate system, it has dimension, 2.3. So Grasberger wrote a comment on one of those two, where, complex or just complicated. Okay, so they, in spite of the fact that the first 5 letters are the same, they mean different things, One is that it's hard to understand, and the other one is that it behaves in interesting ways.
Any other questions or comments? Yes.
Can I ask, you didn't talk about the economic
No,
part.
but I can if you want.
No, I was wondering, what about political systems? I mean, we see this very big change going on right now.
No,
Is-
please.
is-
No, I haven't done that yet. But of course, the behavior of educated populations in addressing socioeconomic problems is not terribly logical. I mean,
But that's the main part missing right now.
well, I know very well, and you see, it's very interesting because it motivates, unfortunately, the behavior of the scientific community. I said the IPCC, that's intergovernmental. There was another thing that was a parallel for the biodiversity. It was called the IGBP. That was International Geobiophysical Program, okay? And it was a program of the international, whatever it's called, I think ICSU, the International Scientific Union, So, but it was something like its organizational status was that essentially of that of an NGO, not of a governmental thing. And I think that it did very good work, and it actually stopped at some point. The final report was much more, in German I would call it nüchtern, comes not to me in English, sort of calm, okay, very objective, scientific. The IPCC is so driven by the need to convince, okay, that I don't think that its politics are very good, because it comes over as trying too hard. To the point that I myself, I was never involved in the actual, it's hundreds of people and thousands of pages and so on. I was a reviewer of the summary for policymakers for, I think, the first and the second one, but after that, I had a problem with it. But on the other hand, I'm lucky enough to have a secondary residence in the Chamonix Valley, and I'm looking at global warming, off my terrace. I mean, the holes in the snow, and the mountain guide with whom I climbed for I don't know how many years always tells me, we were lucky, we did these beautiful things that you no longer can do these days. Because for those who are not aware, before you do a climb, you have to get there. And that used to be snow-covered and relatively easy to go up. But now it's scree, it's little rocks, and it takes forever and a day, okay? So it's there, it's accelerating actually in ways that none of these big models tell us about, okay? So I don't know what to do about that. I wish I did. But it's a very good question.
And I think also you shown in the 1989 paper with Robert Votard that you use in the singular spectrum analysis, and you saw an increasing trend just 30 years ago.
Yeah.
Which was not in agreement with the model. But using observations.
Well, so it goes. I'm not complaining, No, it's amazing, this sort of thing that the geosciences community does not operate in the same way that the physics community operates. In physics, when you have a theoretical prediction and an experiment shows it right, Einstein said you can never, no matter how many experiments, can't prove me right. One experiment can prove me wrong. Never mind. I don't know how many Nobel Prizes for having demonstrated that a certain theory does work, okay? Well, when Snowball Earth was discovered by geochemists, none of those people had read the papers that predicted it. We were the people who worked on that in the middle of the 70s, in the mid-70s, were laughed off the face of the earth by colleagues who said there never was such a thing, Okay, and then there was discovered that it was. Nobody said, "Oh, it would," it was predicted. Okay, and there are other things like this that I won't go into.
Yeah, also because as you always say that all models are wrong, but some one are useful.
More useful box. I mean, it's one of those. Again, the German expression comes to mind, geflügelte Worte. Expressions that that are well known and they are attributed to many different people. But in particular, Box and Jenkins has been credited with that statement.
Other questions? Or okay, so we can thank again Michael for this. And so I think now it's time for lunch outside the door.
Somebody mentioned, papers that tell you how to combine machine learning with physical principles and so on. There is one, I don't know the guy but there is one by a former postdoc of mine, Bach is the composer. His first name is and it's in James. Advanced modeling systems that says how